Hi everyone, my name is Zitian. Today I'm going to present our CVPR paper, Modular Designing Mixture of Experts as Modular Multitask Learners. Our paper focuses on multitask learning and to develop a strong foundation model that can be efficient at downstream. Modular presents a new technique to modularize the unified model into several high-performing components that can specialize for a small set of tasks. In our paper, we first introduce a modular multitask learner. It can develop sparse and strong dependence between expert and task, and then later we show how we can utilize this property to do pruning without any training performance job for each task. We also show it is an efficient multitask learner at scale. Let's start with the definition of multitask learning. Multitask learning aims at learning a single shared model that can perform multiple different tasks at the same time. The good thing of multitask learning is that it can allow us to learn a model that can benefit from the structure among tasks and to develop a strong foundation model that can be later utilized on a lot of downstream applications. The main challenge in multitask learning is that the gradient from different tasks can be contradictory. For example, one task wants to go one direction and the other task may want to go to the opposite direction. The key in multitask learning is model design. We can either sharing parameters between related tasks, or we can specialize on expert for a specific type of data, which we call specialization. The previous solution is to manually assign every model part to a set of tasks. There are two drawbacks of this solution. First, it needs heavy manual effort. You need to design the whole model. The second is it made the model hard to benefit from state-of-the-art network design. For example, you design a CN-based multitask model, and then when the transformer come out, it is hard. You need to redesign the whole architecture, and it is hard to apply the new technique. In our paper, we have a concept expert group that our model is consist of several experts, and each expert construct a mini part of the model that can be shared among tasks or be specialized for one task. We want each expert to learn which task it wants to solve automatically. For example, if we are using expert 1, it is very likely we're doing task A, and if we are doing task B, we are very likely to use expert 3. We want this to happen automatically. Here is a quick preliminary of mixture of experts. In mixture of experts, we have several experts and a router. The output of the MOE module is the weighted sum of the expert, and the weight is produced by the router. The router will only produce K non-zero weight, and it is used to weighty combine the output of the expert. The expert can be any network, for example, NLP or attention network. So here is our modular multitask learner. We have a normal vision transformer, and we customize mixture of expert into it. So we have mixture of expert attention layer and mixture of expert MOEMP layer. And it is supposed to solve multitask learning, and it will have multiple task head for different tasks. And generally, it's just a vision transformer with mixture of expert. So the key in our model is how to assign expert for each task. We only want to learn our model once, and how can we automatically assign expert for each task. Here we introduce a joint probability model over task and expert. We introduce a probability of P E given T, which means that the probability of using expert E when we are doing task T. This can be calculated by counting what the router output. For example, if the router are continually output high probability for the expert E when doing task T, then it have a high probability of doing that. So we can just sum up the router weighting over all the training example to calculate PE given T. After we have the PE given T, we can calculate the mutual information between task and expert. we can use the mutual information formula and have a mutual information here, which is defined, which can be calculated using P E given T. And what does the mutual information doing here is to maximize the mutual dependence between expert and text. So for example, it wants that if we are using expert 1, we are very likely to do text A, and if we are doing text B, we are very likely to using expert 3. So here is a visualization of how this works. For the normal MOE structure here, the expert and all the expert will likely to be used for all the text. And for here, the x-axis is the expert and the y-axis is the text. And if we use mutual information loss here, we can achieve something like this. It has a high mutual dependence between the expert and text. So, for example, if we are doing object classification, we are likely to using expert 1 and 3. It is a very sharp and sparse relation between them. We can also define the class similarity by the frequency that two texts are sharing expert. For example, if text A and text B are likely to sharing a lot of expert, we consider them to be more similar. As you can see from this map, we can then visualize the class similarity between all the texts. And from this map, some interesting finding is that for all these 3D texts at the lower right corner, they are very likely to sharing the expert, so they are more similar. Another good thing of this sparsity and sharpness in the expert-text relation is that we can do pruning for each text. For example, we can remove all the experts that are not used for the classification text, or just remove all the experts that have a low frequency to use. This can save us a lot of model parameters. So basically, without this, we can remove half of the expert without any performance drop by doing this. So a quick summary, we propose a new modular multitask learner, and we show how to develop a sparse and strong dependence between expert texts, and we also show how we do pruning without any performance drop by utilize this property, and we also demonstrate its efficient at multitask learning at scale. Please check our paper for further details. Thank you.